After a brief introduction of relativistic mechanics, today we are going to discuss a very important problem of special relativity, or you can say the relativistic dynamics. This is actually regarding the relativistic mass variation. Actually, in classical physics or in Newtonian physics, there is an assumption that mass of a particle is independent of the velocity of the particle. It means mass of any particle does not depend on its state of motion, that is, what is the velocity of that particle or that object with respect to the observer. That does not matter while we measure the mass of the particle. But in relativistic mechanics, we will see that actually mass is velocity dependent. It means if a particle is at rest, then its mass, and when it will move, then its mass will be different. So in fact, in this lecture, we are going to discuss this relativistic mass variation. And in fact, here we will consider a proper problem of collision between two particles. And this is actually based on a hypothetical experiment. And this experiment is actually due to Tolman and Lewis. So now you can see what in this experiment actually has been told. Let us see here. There are two inertial systems. One is S and another is S prime. And you can see from this figure that S prime is moving towards this frame S with a constant velocity v. In other words, you can say that this S prime is approaching this reference frame S. And see this figure. Actually, this P is a particle attached to the y-axis of this frame S, and Q is an identical another elastic particle attached to the y-axis of the coordinate system S prime. And as you can see, with respect to the frame S, this particle P is moving in upward direction, let us say with a velocity uy, and this Q in its own frame is moving with a velocity, let us say u prime, which is actually equal to minus uy. It means in their own frame, the velocity of these two particles P and Q are equal in magnitude but opposite in direction. Now, as this frame S has been assumed to be fixed and S prime is moving towards it, so definitely after some time this S prime will coincide this frame S. And let us consider when these two frames get coincided, then there is an elastic collision between the particle P and the particle Q. But this collision actually takes place on the line of y-axis. It means center of collision lies on this y-axis, and you can see this situation just here in figure. I have mentioned that just before collision, P is moving up with velocity uy, Q is moving down with velocity minus uy. This is the situation just before the collision. Since, as I have told you, that these particles are actually identical, and so when we measure the masses of these particles in their own frame, the masses will be in fact same. And let us consider that m naught is the mass of each particle when they are at rest. It means this is called actually rest mass. And when they will move with a particular velocity, let us say v, then its mass becomes, let us say, m. Actually, in this problem, we are going to find a relation between this mass m with this mass m naught. M naught is called rest mass, and m is the mass of the particle moving with velocity v. Actually, when the collision will take place on this y-axis and the center of collision lies on the y-axis, in fact, in that condition, due to the impulsive force acting on the particles during collision, the velocity in velocity in x direction and z direction will be not affected. Due to the impulsive force, only the velocity in y direction of the particle will be affected because the center of collision lies on y axis. And so you can see in this figure that I have shown here that just after collision, the velocity of p is now minus uy. It means p will now move downward, and q is uy. It means there is just an exchange of velocity, and this is actually obvious since masses of two particles are same and collision is elastic. So you have definitely studied in mechanics that if the two bodies of same mass collide elastically and the collision is one dimensional, then simply there is an exchange of velocity after collision. So here I have shown that just after collision, velocity of p is minus uy and velocity of q is uy. Actually, we will discuss this problem by using the concept of momentum conservation. And you know, momentum of a colliding system remains conserved but in a particular frame. So you can apply the momentum conservation principle either in frame S or in frame S prime. Let us consider here we will deal with this conservation principle of momentum in frame S. And you know, if we want to apply the momentum conservation principle in this frame S, then definitely we must have to know the velocity of the colliding particles, that is p and q, in frame S. So for that we will use actually the velocity transformation equation. You can see I have mentioned all these things here which I have actually just told you. So to get the momentum of colliding bodies in frame S, we will use actually the velocity transformation equation, and you know that velocity transformation, in accordance with the velocity transformation equation, the x component of velocity with respect to frame S, this is ux, and that is equal to u prime x plus v over 1 plus v by c square u prime x. And uy is u prime y into root over 1 minus v square by c square over 1 plus v by c square u prime x, and similarly uz is equal to this much. Now using this velocity transformation equation, we will actually find the velocity of the particle q in frame S, because you know the velocity of particle q in frame S prime, and then we will actually calculate the momentum of the colliding system in frame S before collision and after collision. So now let us consider let motion of the colliding system, motion of the colliding system in frame S. So you can see here that in frame S, what are actually the components of velocity of particle P just before collision. So components of velocity of particle P just before collision, in frame S. So you can see actually we write it by the symbol uxp. When you write uxp, this is x component of velocity of particle p with respect to frame S before collision. And you know, before collision with respect to frame S, you can see here that particle p is moving in fact in y direction, and as its motion is in y direction, you can see, so its so x component of its velocity and z component of its velocity will be 0. So you can see this will be 0. And again, what will be actually the y component of its velocity? We have assumed that this particle p is moving with velocity uy in positive y direction. So actually this uyp is simply equal to uy. And as the particle has velocity with respect to s only in y direction, so its z component will be also 0. So these are the components of velocity of particle p, you can say uzp, components of velocity of particle p with respect to frame s just before collision. Now see, for particle p, for particle q, now we are talking for particle q. You know, before collision, components of velocity of q in frame s prime, remember, in frame s prime, not in s. So what are those values? We will actually write these velocity components as u prime x q. Since in frame s prime you can see this particle is moving along this y-axis in downward direction, so definitely its x and z component with respect to frame s prime will be 0, just like p as you have seen in frame s. So u prime xq will be equal to 0. Again you have considered that the y component of this particle, the velocity of this particle q with respect to frame s prime is actually equal to minus uy. And since it has velocity with respect to s prime only in y direction, so definitely the z component of its velocity with respect to s prime is also 0. But remember, we have to know all the components of velocity with respect to frame s, because we are going to apply the conservation principle in frame s. So we must have to know the velocity component of both of the colliding particles in frame s, not in frame s prime. But you know the velocity components of the particle q in frame s prime before collision. So you can use these velocity transformation equations, and using these velocity transformation equations you can find the components of velocity of particle q in frame s. So if uxq, uyq and uzq be the components of velocity of q in frame s before collision, then using these velocity transformation equations you can find these velocity components and so what will be now this uxq? You can see this formula uxq. When you say uxq, it means here will be u prime xq, and you can see u prime xq is equal to 0. You can see here, so this is 0 plus v and over 1 plus v by c square u prime xq, but u prime xq is 0, so this will be simply v. So before collision, x component of velocity of particle q with respect to frame S is actually equal to v. Now again we will find actually the y component of its velocity with respect to frame S. We know its y component of velocity with respect to frame S prime. It is known to us. It is known. But we have to find the y component of velocity of particle Q in frame S, and for that we will actually use this velocity transformation equation. You can see u prime y means u prime y q, and that is actually minus uy. So uyq, what will be now this uyq? You can see from here. This will be in fact u prime yq into root over 1 minus v square by c square and divided by 1 plus v by c square u prime xq, u prime xq. But you know this is in fact u prime xq. This is x. So you can see this u prime yq, as I have mentioned here, this is in fact minus ui, and u prime xq, you can see it is 0. So this will be minus uy root over 1 minus v square by c square and divided by 1 plus 0. So this is simply minus uy into root over 1 minus v square by c square. And similarly, when you will actually calculate the value of uzq, you know uzq in accordance with the velocity transformation equation will be u prime zq into root over 1 minus v square by c square over 1 plus v by c square u prime xq. But you know this u prime zq, you can see it is in fact equal to 0. So if it is 0, the whole result will be 0, and so this is 0. So we have calculated the x, y and z component of velocity of particle q, and x, y and z component of velocity of particle p are already known in frame S. So now we can actually calculate what will be the total linear momentum of the system p plus q just before collision in frame S. So total linear momentum of the system P plus Q in frame S before collision. If we denote it by this symbol pi, so you can see what will be this. Actually this will be before collision linear momentum of p, so this is pip plus before collision linear momentum of particle q. Now you can see what will be actually the values of these momentums. So as you can see here, the velocity of the particle p, in frame S before collision. In fact, x component of velocity is 0, is z component is also 0. So it will have momentum only due to this y component. And since this velocity is measured by the observer situated in the frame itself, so we will write then while calculating the momentum, we will write the rest mass of the particle. Rest mass of the particle. And so, what will be the momentum of P? This will be actually m naught into uy, and it is in y direction, so we write the unit vector j hat. And plus, now piq, you can see the x component of the velocity of q with respect to frame s is v, and as with respect to as this particle is moving with velocity v, and we have assumed that when the particle will move with velocity v, then its mass is m. So this will be mvi, and the y component of this particle is minus uy into this much. So this momentum will be minus m into uy root over 1 minus v square by c square j. This is in fact momentum in j direction, that is y direction. And you can see, since uz q is 0, so z component of momentum of q will be in fact 0. So this is actually the total linear momentum of our colliding system just before the collision. You can see. So what will be the, I have not assumed any equation number, so this is, let us say, equation 1. Now, by applying the same transformation equation, now we will find the velocity of particle P and velocity of particle Q just after collision, again in frame S. So now we will denote this velocity by, let us say, some another symbol, let us say in fact W. So you can see just after collision, just after collision, components of velocity of P in frame S. Let us say now we denote the velocity by the symbol W so that you do not confuse between the velocity before collision and velocity after collision. So now let us write Wxp is the x component of velocity of particle P just after collision in x direction. But you know, you can see the figure, just after collision our particle P is moving in negative y direction with velocity minus uy with respect to this frame S. Since its velocity with respect to S is in negative y direction, so definitely z and x component of its velocity will be 0. So what will be this Wxp? This will be simply 0. And also you can say that Wzp will be also 0. Only one non-zero component of its velocity is what? That will be Wyp, and this Wyp is now minus uy. So these are the components of velocity of particle P just after collision in frame S. Now let us see what are actually the components of velocity of particle Q in frame S prime. So after collision, components of velocity of Q in frame S prime. In frame S prime, remember, in fact in frame S prime after collision components of velocity of Q we write W prime xq, and as you can see, after collision this q is now moving up. You have seen earlier this q is moving up with velocity uy with respect to frame s prime. So since velocity is in y direction with respect to s prime, so x and z component of velocity of this particle q will be 0. And so w prime xq, this is actually 0. Similarly, w prime zq will be also 0, and only w prime yq is now uy. This is uy. As you have seen, this is now uy. So now we will find by the use of velocity transformation equation the x, y and z component of velocity of this particle q with respect to frame s, because we have to find the total momentum in frame s, not in frame s prime. So if wxq, wyq and wzq be the components of velocity of q in frame s, not in s prime, in frame s, then using the same transformation equation you will find that wxq. In fact, I am leaving for exercise to you, and I am going to write directly these values. You will find that this wxq, let us see once again. When you will find wxq, you can see this transformation equation. In fact, this prime value will be 0, this is 0, so this will be simply v. So this will be actually equal to v. So wxq, this will be v, and wyq, what will be this wyq? Using the velocity transformation equation, you can see that this will be uy into root over 1 minus v square by c square. You can check it from that transformation equation. And wzq, since this w prime zq is actually equal to 0, so this whole result will be 0. So this is actually 0. So now you know the x component, z component and y component of velocity of particle p after collision in frame s, and you also know the x component, y component and z component of velocity of particle q after collision in frame s. So now we can find the total linear momentum of this colliding system p plus q after collision in frame s. So after collision, the linear momentum of the colliding system p plus q in frame s. You can easily see that if we write it as pf, then this will be pfp plus pfq. And you can see what will be actually the values of these momenta. This will be actually equal to minus m naught uyj. In fact, this is pfp minus m naught uyj. And this PFQ, this will be plus MVI and plus MUY root over 1 minus V square by C square J. So this is actually the total linear momentum of the colliding system after collision. So now, according to the principle of conservation of linear momentum, these two momenta will be same. So by momentum conservation, by momentum conservation, Pi will be equal to Pf, and you can see this will be m naught uy j. We have actually calculated here the value of Pi. You can see from here, this is in fact Pi, and you should put the value of this Pi. And this is m naught uij plus mvi minus muy into root over 1 minus v square by c square j. And this will be equal to Pf, and Pf you can see here, this is Pf. This is minus m naught uy j plus mvi plus muy root over 1 minus v square by c square j. Now you can simplify this equation. You can see this mvi and this mvi in both sides will cancel out, and from here you can get that 2m naught uy, this will be equal to 2m uy root over 1 minus v square by c square. And so you can say from here, you can see first of all here that this 2 factor will cancel, this uy will cancel, and so you can easily say that mass m of the particle when it is moving with velocity v is equal to m naught over 1 minus v square by c square's square root. And this factor 1 over root over this much is also written as gamma, so you can write this expression gamma m naught. So this is actually the famous mass variation formula, relativistic mass variation formula. From here you can see easily that if v increases, you can see this result. If v increases, then this factor will decrease. So if denominator will decrease, the result will increase. So if v increases, then m increases. So with increase in velocity, mass of the particle increases. And if you consider that if v tends to c, in fact, in that condition, you can see that this v by c will tend to 1, and so this implies this if v by c is 1, then this denominator will be actually 0, and so the mass m will then tend to infinity. So if any particle is capable to move with a velocity equal to velocity of light c, then mass of that particle will become infinity. But as you know, according to special relativity, no material particle can move with a velocity equal to c and greater than c. So definitely mass is finite. It is never in fact infinity in practice. So this is mass variation. But if you consider that this v is much smaller than c, this is in fact classical limit. In that condition, you can neglect this v square by c square in comparison to 1. So in that condition, actually m will be equal to m naught, and this is our classical result. So actually this mass variation will be experienced only when we are talking about a speed which is comparable to the speed of light. So this is in fact mass variation formula, and you can see this variation graphically here. If you write v over c on this horizontal axis and m by m naught on this vertical axis, then when this v by c will be in fact 0, you can see m will be equal to m naught. It means that this ratio will be 1. So in fact this graph is almost like this. In fact this point indicates that here v is almost equal to c, that is 1. So this is the graphical variation of mass against of velocity. And so you have seen from this result that mass is actually velocity dependent in accordance with special relativity. Actually, we will discuss this result to some extent, and we will